Hi, in this video, we'll be talking about electric fields. An electric field is a region around a charged particle or object within which a force would be exerted on the other charged particles or object. Basically, the electric field is an area around a charged particle where there is a potential of a force being exerted to another charged object or to another object that is within the reach of that electric field of a specific charged particle. Electric force is a non-contact force, which means that even though there's not direct physical interaction or direct touch between the two particles, since it's a non-contact force, even at a distance or even in a distance, your electric force can be exerted by a charged particle as long as it's in the electric field. Electric charge Q can exert a force on other objects even though they are not at some, or even though they are at some distance away. And the space surrounding a charged particle is known as the electric field, which is denoted by the capital letter E. Now let's talk about electric field lines. Michael Faraday, an English scientist who made important discoveries on electricity and magnetism, introduced the use of electric field lines to map out an electric field. Now what are the things that we need to remember when we look into electric field lines? So these lines of force have the following properties. A line of force starts from a positively charged particles and end on negatively charged particles or continue toward infinity. When the charge is positive, the direction of the electric field is away from the charge. If the charge is negative, then the direction of the electric field is towards the charge. So if you have a positively charged particle, electric field lines will diverge out of that charged particle. And if the charged particle is negative, all electric field lines will converge toward that negatively charged particle. Electric field lines neither intersect nor break as they pass one charge to another. And the greater the number of field lines, the stronger the electric field. When we draw electric field lines, when we want to represent a stronger electric field or a strong electric field, then we have more field lines, electric field lines. The neutral point is the point where no lines of forces pass. The electric field is zero at the neutral point. So when we look at these illustration, as what we have mentioned in the properties of electric field lines, you have there the first illustration, a positively charged particle. So you have there the electric field lines diverging from that uh, charged particle. And then we have the isolated negative charge. The electric field lines are moving towards that electric or moving towards the particle. Here, again, for the positive, it's diverging or moving away. Now, if there's a one positively charged particle and one negative charge, as we have mentioned, your positively charged particle will have diverging electric field lines moving away from the particle. And since your negatively charged particle, the electric field lines are moving towards that negatively charged particle, so this will be the correct illustration of the electric field lines when you have one negative and one positively charged particle. And remember, your electric field lines neither intersect nor break, so it's a continuous line. If you have like signs, such as two positive charges here, it will look like this one. Now, since your positively charged particles, for these positively charged particles, electric field lines diverge out of the particle. Therefore, you will have here a neutral point where no electric field lines pass. So this is how you illustrate electric field lines for isolated positive charge, isolated negative, if you have opposite signs, and if you have positively, if you have if you have like particles, like charged particles. If this is negative, then your field lines will just be converging towards the particle if it's negative. Now, the electric field due to a point charge. Electric field is again defined as the force that a test charge will experience when placed at that point. At specific parts of the electric field, the a test charge, or the charge subject to the electric field of another particle, will experience a different electric force if placed on different parts of the electric field. Physicists use a unit, positive charge, as the test charge in defining an electric field. And this test charge and electric field are usually represented by Q sub 0 or Q0 and E respectively. So we have the E, or electric field, is equal to K, and the absolute value of the charge of the test charge divided by R2, or the distance between the distance between the test charge and the position of the point where we want to measure the electric field. So let's have here an example. An electric dipole consists of two equal but unlike charges separated by a distance of, as you can see here, 6.4 times 10 raised to negative 12 meters. 2-point charges, Q1 is positive 4.5 times 10 raised to negative 6, and Q2 is, since as mentioned, it's equal but unlike, so it's negative 4.5 times 10 raised to negative 6 coulombs, which are separated at a distance of 6.4 times 10 raised to negative 2 meters, forming an electric dipole as shown in this figure. Find the electric field if the point that we are to consider is halfway between this dipole. So this is your dipole, the two charges, and we are to measure the electric field here. So this is our point to solve for. Now, how much will be the electric field experienced in this point? So what are our given values? Again, you have your Q1, which is positive 4.5 times 10 raised to negative 6 coulombs. And then the charge for particle 2, that's negative 4.5 times 10 raised to negative 6 coulombs. And we have the distance, no, between the two particles, which is 6.4 times 10 raised to negative 2. Now, again, looking into it, this point here will be affected by the electric field due to Q1 and electric field due to Q2, which means that we need to solve for the electric field due to Q1 and due to Q2, and will solve for the resultant electric field that will be experienced by this point here. So solving for the electric field due to Q1, and our formula again is electric field is equal to K, or the Coulomb's constant, times the test charge over R2, or the K is equal, E is equal to the Coulomb's constant multiplied by the charge of the particle divided by R2. So E will be 9, E1 will be 9 times 10 raised to 9 Newton meter squared per Coulomb squared, times the charge, which is positive 4.5 times 10 raised to negative 6, that's absolute value Coulomb, divided by the distance. Now the distance between this point and Q1, What would be the distance between this point and Q1? Since we have 6.4 times 10 raised to negative 2 as the distance between Q1 and Q2, and this point here is halfway, then the distance between the point and Q1 will be half of the distance between the 2 points. And that distance will be, of course, it's 3.2 times 10 raised to negative 2 meters if you divide that by 2. So that will give us 3.2 times 10 raised to negative 2 meters squared. Now, so we have here, we canceled this one and this one. Your electric field due to Q1 will be equal to 3.96 times 10 raised to 7 newtons per coulomb. And for E2, or the electric field due to the particle 2, that's 9 times 10 raised to 9 Newton meter squared per coulomb squared times the absolute value of negative 4.5 times 10 raised to negative 6 coulombs over same distance between, because this is halfway between the positive and the negatively charged particle. That is 3.2 times 10 raised to negative 2 meters squared. Cancel this one and this one. So the electric field due to particle 2 is also 3.96 times 10 raised to 7 newtons per coulomb. Now, what will be the electric field that will be experienced by a charge that is placed, by a particular charge that is placed halfway between Q1 and Q2? If you remember the concept of electric field lines, a positively charged particle will have electric field that is moving away from the charge, and negatively charged particles will have electric fields moving towards it. So what does this mean? This particle here will experience an electric field that will, if we assign directions, the electric field experienced by a charge at this point from the positively charged particle will be due to the right, as well as the electric field that will be due to Q2 is also due to the right. So if that's the case, then the vector sum, since both of them are going towards the same direction, the vector sum of the electric field experienced at this point here, at midway, or halfway the positive and negatively charged particle, so that's E1 plus E2. Substituting our values, we know that it's 3.96 times 10 raised to 7 newtons per coulomb, and it's positive due to the positive side, going to the right. Plus, it's also positive 3.96 times 10 raised to 7 newtons per coulomb. Since, again, the positively charged particle will have an electric field towards this direction, with respect to this point, and the negatively charged particle will also exert, or will have an electric field due to the same direction. So your total electric field experienced midpoint of the positive and the negatively charged particle, it's 7.92 times 10 raised to 7 newtons per coulomb, which is positive or directed to the right. Directed to the right. So what does this mean? What does 7.92 times 10 raised to 7 newtons per coulomb mean? For every 1 coulomb of charge, the particle in that electric field will experience an electric force of 7.92 times 10 raised to 7. So that's our sample problem 1. Let's look into another sample problem. 2-point charges with Q1 with a charge of 4 microcoulombs and Q2 with negative 2 microcoulombs are arranged as shown in the figure. So we have here the positively charged Q1 placed along the y-axis, and you have your negatively charged Q2 placed along the x-axis here. If L here, the distance between this point and the positively charged particle and this point and the negatively charged particle are both 3 centimeters, so these are 3 centimeters, what is the electric field due to the origin? So let's solve for the electric field due to this point. So again, let's list the given values. You have your charge at Q1, which is 4 microcoulombs, and Q2, negative 2 microcoulombs. Now, remember that our Coulomb's constant, since our electric field formula is K multiplied by the charge divided by R squared, our Coulomb's constant is expressed in Newton meter squared per Coulomb squared. So all our values must be expressed in the same unit. Now we need to convert this one into Coulomb, and we know that micro is 10 raised to negative 6. So we can rewrite this as positive 4 times 10 raised to negative 6 coulombs, and this one negative 2 times 10 raised to negative 6 coulombs. And we have your R, or the distance at the origin, point of origin, which is equal to both Q1 and Q2. So let's just express it as R. So R is 3 centimeters, but we need to express R as meters. So we need to convert that, and 3 centimeters is equal to 0.03 meters. So since there are two particles, positively charged and negatively charged particles, this point here will experience an electric field due to Q1 and due to Q2. Therefore, we need to solve first for the two electric fields caused by Q1 and caused by Q2. So solving for the electric field due to Q1, so that is, again, Coulomb's constant, 9 times 10 raised to 9 Newton meter squared per Coulomb squared, multiplied by the absolute value of the charge over 0.03 meters squared. That's, let us rewrite that one. So multiplied by 0.03 meters squared. And the electric field due to Q1 is 4 times 10 raised to 7 newtons per coulomb. And since we have here, if you look at Q1, it's positively charged, therefore it will have an electric field moving away from it. Therefore, this point here will experience an electric field, if we look at it in the Cartesian coordinate plane, going down. So directed downward. For E2, so you have the same formula, 9 times 10 raised to 9 Newton meter squared per Coulomb squared, multiplied by the charge, which is the absolute value of negative 2 times 10 raised to negative 6 coulombs, divided by 0.03 meters squared. Now, the electric field due to E2, or the electric field due to Q2, is 2 times 10 raised to 7 newtons per coulomb. Now, since this is negative, the negative charge here, our electric field will be moving towards it. And since it's moving towards it, your electric field here experienced at the point of origin is directed to the left. So that is our those are our two electric fields experienced at this point. So if we illustrate that, if we put here a particle or charged particle, at that point there will be an electric field going down and going to the left. And remembering your lessons on vectors, if we have here a field that is due downward and due leftward, we can solve for the resultant or the vector sum of all of the electric fields, which will be at this point. So how will we solve for that? If one is going down and one is going to the left. So the magnitude of the resultant electric field can be determined with the use of the Pythagorean theorem. And the direction, of course, we need to identify its direction, will be or can be identified with the arctangent function. So you must be able to remember your lessons in vector addition. So solving our resultant electric field, so that's E is equal to, using the Pythagorean theorem, that's the square root of E1 squared plus E2 squared, which will give us square root of 4 times 10 raised to 7 newtons per coulomb squared plus 2 times 10 raised to 7 newtons per coulomb squared. So the electric field experienced at the point of origin is 4.47 times 10 raised to 7 newtons per coulomb. And its direction, the direction of the electric field, will be the arctangent of E1 over E2. When we look at it, this is E1 and this is E2. And our angle is here. And if your E1 is opposite and E2 is adjacent, so we will have this formula to solve for the angle, which is arctangent E1 divided by E2. So substituting our values, that's arctangent 4 times 10 raised to 7 newtons per coulomb over 2 times 10 raised to 7 newtons per coulomb. So your direction will be 63.43 degrees. And again, if we look at here, this one will be, since this is west and this is south, since going down and going to the left, we can label the direction as south of west. So that's south of west. Therefore, if there's a particle here, it will experience it will have an electric field. This point here will have an electric field of 4.47 times 10 raised to 7 newtons per coulomb, 63.43 degrees south of west. For every 1 coulomb of charge, it will experience a force of 4.47 times 10 raised to 7, directed 63.43 degrees south of west. So that's it for our lesson in electric fields. Thank you very much for watching this video.